Okay, welcome to episode 2 of the Science of Setup. What we're going to talk about in this this episode is the suspension properties, what they are, what they mean, and how you can use them to help understand making setup changes. So first thing is we're going to be using RC Crew Chief for this. So if you want to follow along, you should use the link that's on the Live RC page and download and install this version of RC Crew Chief. This version contains 7 different models that we'll be looking into as we move through this series. So if you want to follow along and learn how to click through RC Crew Chief, I would highly recommend that you download the program. It's a fully functional. The trial period is currently unlimited, so you can get through all the episodes here without having to even worry about purchasing the program. So onward. We're going to work on the setup page. That's pretty much specifically what we're going to deal with here today. So you'll see on the side here are suspension properties, and this is what we're going to be talking about. So first off, we're going to start at the top and work our way to the bottom. So the first thing on the list is the roll center. The roll center in RC Crew Chief is measured relative to the ground. So a negative value means that the roll center is below the ground plane. A positive value means it's above the ground plane. Lowering the roll center increases the amount of roll moment, as you saw in the first episode. So that increases the amount of chassis roll that you're going to see, that you're going to have to use your shocks and springs to control. So let's just have a quick look here at what affects roll center. Essentially, the main thing are the angles and positions of the suspension arms. So by raising and lowering our inner point here, you're going to see if I raise it up quite a bit, the roll center has now dropped. The other thing that you need to keep in mind when you're doing this is that you can't make a change in one area without affecting something else. So by doing that, we have lowered the roll center. We have decreased the chassis roll sensitivity, which we'll talk about in a minute. And we've also decreased the amount of camber gain that we're going to have. So making one change, you need to understand that it may affect you someplace else, and the change that you're expecting to see in the handling may not be exactly what you expect because you have changed something else that may have a more dramatic impact on the handling than what the change you made or were anticipating had. So the other area where you can make changes to the roll center is with the lower suspension arm, and actually making changes here has a more dramatic effect on, let's just reset this back to where we started. So here, if we go from 0 to a 2 millimeter shim, we've changed the roll center by, let's call it 1.5 millimeters. Now if we do the same thing to the lower suspension arm, if we move it by, let's move it by 1 millimeter, you'll see here that we made quite a big change, over 2 millimeters. So essentially what I'm trying to illustrate here is that changes to the position of the lower hinge pin have a more dramatic effect than changes to the upper link on the roll center. The upper link has a bigger impact on camber gain, which we'll talk about in a few minutes. Okay, next is what's called ride stiffness and ride frequency. We'll look at these together because they are very closely tied together. The ride stiffness is essentially the vertical stiffness due to the springs. So when you poke your chassis when it's sitting on the bench and you press down on it, that's what you're feeling, is the ride stiffness. The ride frequency is the frequency that the suspension would oscillate at if there was no damping. So let's have a quick look at what we can do here to adjust our ride stiffness. Reset it again. So ride stiffness is primarily affected by our shocks and our shock angles. So by changing springs, so if we change a spring, we go to a stiffer spring, that's going to increase our ride frequency. If we stand our shock up, that's going to increase our ride stiffness and our ride frequency. Similarly on the rear, we stand up our rear shock. Now we've increased our ride frequency on the rear as well. Now, one thing about ride frequency is generally you want these numbers to be fairly close together, and particularly the rear should be slightly higher frequency than the front. This is more important in off-road applications where you're dealing with a lot of bumps. On-road where it's a smooth surface, it's not as critical. So that's ride frequency and ride stiffness. Okay, up next we're going to talk about roll properties. So we have a roll stiffness, we have a roll couple, and we have a roll sensitivity. And these are listed here on the suspension properties table. So roll stiffness, there is a contribution due to the springs and a contribution due to the anti-roll bars. The sum of those two numbers gives you the total roll stiffness of the car. The things that affect these values are the springs themselves, obviously, the angle that you have the shock at, whether laid down or stood up, and the anti-roll bar as to whether it is a stiff anti-roll bar or a soft anti-roll bar is going to make a difference in the value here. Next is the front to rear roll couple, and this is a very good indicator of whether you're going to be moving the car's handling towards over or understeer. So what it is it is just the ratio of the front roll stiffness to the total roll stiffness gives you this roll couple expressed as a percentage. So if this number is 50%, that would mean that the front and rear roll stiffness are exactly the same. If the roll couple is less than 50%, that means that the front is softer than the rear, and you're going to have a handling tendency towards oversteer, or loose, as it's sometimes called. If that value is greater than 50%, then you are going to have a handling tendency that is going to be towards understeer or push. Now, the chassis roll sensitivity, this is a value that indicates the overall stiffness of the car. It basically equates the rolling forces, the rolling moments, to the resisting forces, which are your springs and anti-roll bars. So it's a very good indicator as to how responsive the car is going to be. The smaller this number is, the more responsive the car is going to be. You would say, well, why not make this number as small as possible? Well, the smaller you make it, the harder the car becomes to drive. So you'll see in later episodes this number can vary from as low as 0.5 for a 8 scale on-road car to 4 or 5 for off-road vehicles. So once you have a good handle on where this number needs to be, you can use it to your advantage to make sure that the handling characteristics of your vehicle aren't going to be too difficult to control. So what can we do to change these values? So as I said, the roll stiffness is controlled by the springs and the shock angles. So if we change a spring rate. Let's go up a couple. So we went from a 2.6 to a 2.8 Newton millimeter spring. So you can see here that the roll stiffness due to the springs has changed. The red value is what it was. The black value is what the new value is. So we have increased the total roll stiffness, which has changed our front roll couple. It's moved it up higher, closer towards 50%. So we went from, we're adding less oversteer by doing that. The other thing that we did is we stiffened the overall chassis a little bit. This number's gotten a little smaller, so that means that the overall roll sensitivity is less, which means the car would be slightly more responsive. The other thing we can do is we can stand our shocks up. So standing the shocks up, again, I have increased the total roll stiffness of the front, which has moved this roll couple so it's greater than 50% now. So that would mean that the car would probably be more towards a push or an understeer condition as opposed to a loose or oversteer. And again, we've also increased the roll sensitivity, so the overall stiffness is increased. The other thing we can do is we can change our anti-roll bars. So we go to a stiff anti-roll bar, and there you can see that we've increased this value. So our anti-roll bar contribution has increased the total roll stiffness. And again, we've gone higher in the front to rear roll couple and stiffer in the roll sensitivity. Okay, so next we're going to talk about camber. We have basically two parameters here. We have a static camber setting. This is what we set when we've got our car sitting on the bench, and then we have a camber gain value. The static camber is measured at ride height. The negative value means the top of the tire leans inward. Camber gain is measured as a change in the camber due to the vertical movement of the chassis. So you can see here in the second graphic that we've displaced the chassis down, and our -2 degrees of camber has now become -2.8. So in this case, this example, the camber gain would be -2 minus 2.8, which gives you a 0.8 degree of camber gain for whatever value of displacement that we have used here. So if the camber value increases, we have camber gain, and it's a camber loss if it decreases. Normally you don't want camber loss, you want camber gain, because as the chassis rolls, you actually lose camber on the outside tire. So you want to add more camber to counteract that loss as the chassis rolls. So let's just have a quick look here how we can change camber gain. So let's reset this again. So camber gain is controlled by the angle of your arms. The more down angle you have on your upper link, or the more that the upper and lower links converge as they move inward, the more camber gain you will have. If your upper and lower arms are parallel, then you will essentially have 0 camber gain. Now, if the angle between the upper and lower arms is actually getting greater or diverging as you move inward, then you will have camber loss. So quickly, let's zoom in here a little bit, makes it easier to select points. So if we change our upper arm, we lower it, so now the angle of the upper arm is more of an angle toward to the lower arm. You can see here that our camber gain has increased. It's gone from 0.1 to 0.2. We can do similar thing and make it even more. We can raise the outer point. So if we raise the outer point, you can see now we've gone to 0.365. We can also change the lower hinge pin. If we raise this, see we've got our angles are more convergent towards the inside. Now we've gone up to 0.45. So the angle of your upper and lower arms are what change your camber gain. The length of the upper link also affects camber gain, and what it primarily affects is how much the camber gain will change as the suspension arms move. Okay, now we're going to talk about damping that is provided by your shocks. So the shock, number of holes in the piston, the viscosity of the shock oil that you're using, these are all the things that affect your what's called damping ratio. So the definition of damping ratio is the ratio of the damping provided to what's called critical damping. So there's 4 different levels. There's zero damped, which means that the system has no damping in it whatsoever, which is actually an impossible situation because you're always going to have some friction in anything that's moving. But this blue line represents that, so the system would just oscillate indefinitely. There's what's called underdamped, which is where the damping ratio is less than the critical damping value, so the damping ratio will be less than 1. So that's represented here by the green line. So you can see the system responds, overshoots from where it's supposed to be, undershoots a little bit, and then settles to where you want it to go. The critically damped means that the system responds quickly but with no oscillations. So it just goes from the initial position to the final position relatively quickly, but does not have any oscillations. And then there's what's called overdamped, which the system responds similar to the critically damped, but much slower response before it finally gets to where you want it to be. So let's have a look at what we can use in RC Crew Chief to see how that is impacted. So first thing, you can change your pistons in your shock. So if you go to a smaller hole size, you can see here that our damping ratio has gone from 0.5 to 0.7. You can reduce the oil viscosity. So now you can see we've kind of got back to where we were before by going to a lower viscosity oil. Changing your shock angles is also going to affect your damping ratio, standing them up, because this is essentially making the shock stiffer, so it's changing your damping ratio. Those are the primary things that affect the damping ratio. Normally these values are, for an on-road application, are going to be between about 0.4 and 0.6 because you want less damping in an on-road application. You don't have to deal with a lot of bumps and absorbing the impact of bumps. If you're in on a bumpy track, then you may need to run higher damping ratios. Off-road applications, you're going to see these numbers anywhere between 0.8 and 1.2 because you need to have that additional damping so that you can absorb the energy when you're traveling over bumps and landing off jumps and that sort of stuff. Okay, last but not least, steering Ackerman. So steering Ackerman is the difference in the angle between your outside tire and your inside tire. So you can see here with the settings we had in the links for this example, we have a difference of 9 degrees between the inside tire and outside tire at maximum steer angle. In this case, we have 17 degrees difference between the outside and the inside. So this example represents more Ackerman or pro Ackerman, and this example represents less. So it's affected by your tie rod length and the angles between the tie rod and the steering linkage. So more Ackerman, you've got a greater difference between the inside and outside wheel. Less Ackerman, a lesser difference. So in our steering simulation here, you can see we can drag this around and we can see what our actual differences are. We can actually graph them as well. So if we want to look at this example, let's go to the smallest. So there's the most we can get as far as Ackerman is concerned. We've got almost 16 degrees of Ackerman at full wheel or full steer angle. Whereas if we go and we shim this out, so we go to our 3mm shims, now we only have somewhere slightly more than 6 degrees. So you can see you can have a big impact on the amount of Ackerman just by changing the location and the shims on your steering rack. Other vehicles besides this one may have alternate holes on the outer steering hub as well, which also have a major effect on steering Ackerman. We'll look into those a little more later on. Okay, so that's it. Up next, we're going to start looking into more setup details, and we're going to start talking about weight transfer. So we're going to learn how we can adjust and control weight transfer balance and what it's going to do to our handling. So stay tuned for episode 3.